Okay, we're given the problem that 100 grams is moving to the right at 4 meters per second, 200 grams to the left at 2 meters per second. And we're asking questions about momentum and kinetic energy. Okay, well, momentum is a vector quantity. This tells you that you'd better know what your positive direction is. Now, you can make any direction your positive direction. We're going to make this one the positive direction, in which case this 2 meter per second velocity is negative, and that's how we've written it here. And the question did arise in class, do you have to worry about the sign? Well, yes, if you have a vector quantity, you do have to worry about its direction. And yes, momentum is a vector quantity, so yeah, you have to worry about the direction of the velocity. So we calculate the sum of the momenta. The momentum of each is its mass multiplied by its velocity. The first one has a mass of 100 grams, which is 0.1 kilograms, a velocity of 4.1 meters per second, giving it a momentum of 0.4 kilogram meters per second. Okay. The second has a mass of 0.2 kilograms, 200 grams is 0.2 kilograms, multiplied by negative 2 meters per second, and that gives you negative 0.04, or negative 0.4 kilogram meters per second. Now this is 0.4 kilogram meters per second, this is negative 0.4 kilogram meters per second. That adds up to 0. So we see that m1v1 plus m2v2 is equal to the 0 vector. What's the kinetic energy? Well, we do 1/2 mv squared for each. Square 4 meters per second, you get 16 meters per second. Multiply that by 1/10 of a kilogram, and you get 1.6 kilogram meters per second. Then it's, of course, 1/2 mv squared. Half of 1.6 is 0.8, so you get 0.8 kilogram meters per second squared, or 0.8 joules for the energy of this one. The energy of this one, calculated in completely similar manner, you square the negative 2 meters per second, you get 4 meters squared per second squared. Multiply that by 0.2 kilograms, you get 0.8 kilogram meters per second squared, and take 1/2 for the 1/2 mv squared, you get 0.4 joules. These are both positive. Kinetic energy can't be negative. You're squaring the velocity, unlike what you did with velocity here. It had a sign, it had a direction. Here, it's just the magnitude of the velocity. And we add these, we get 1.2 joules. And that's your 1/2 mv1 squared plus 1/2 mv2 squared. That gives you your 1.2 joules. Okay, now, after collision, we used v for velocity before collision. I'm going to use u for the velocity after collision. Well, I'm going to let you verify it. You just do all the same calculations, and you find out that the momentum is still 0. The kinetic energy is still the same as it was before, because if you square 4 meters per second, you get the same thing you get if you square negative 4 meters per second. If you square negative 2 meters per second, you get the same thing as if you square 2 meters per second. And both of those squared velocities go into the calculation of the momentum. Okay, now I had kinetic energy equals 0 because I was thinking, I was answering the question, what's the change in kinetic energy? And I just wrote 0 again because my brain doesn't seem to be connected to my hand. The change in kinetic energy is 0, but this is not the change in kinetic energy. This is the sum of kinetic energies, and it's still 1.2 joules. Same speeds, so the same kinetic energies. Okay, next we ask, what would this collision look like in a new system as observed from a coordinate system that's moving at 3 meters per second in this direction? Okay, what is the speed of this as measured in that system? What's the speed of this one as measured in that system? What are the total momenta before collision, after collision, what's the kinetic energy before collision and after collision, and what's the change in kinetic energy. Now let's make note here that the change in kinetic energy is 0. Change in momentum is 0, and the momentum itself, total momentum itself, is 0 here. Okay, now we'll take up this new system in another video.